Hi, I'm Dr. Emanacker. In this particular video, we're going to take a look at slopes and equations of lines. For students in calculus, this should be a review section. There should not be anything new or surprising here for you, but just a video to brush the dust off of things that you already know. We're going to look at 5 different points in this. First, we're going to look at what a slope is, how to compute it, interpret it, and apply it to situations. These really do apply to real-world situations. We're then going to take a look at what the equation of either a horizontal or a vertical line looks like and how to go about graphing these. Then we're going to get into 2 different equations or forms of equations for a line. The first being the slope-intercept equation, and the second being the slope or the point-slope form. The last thing we're going to do is we're going to then take a look at several applications of linear equations in solving problems. First thing we're going to look at here is slopes. You may recall the equation of a slope being one of several things. One, recall that m is the abbreviation for slope, and it is identified as being the change in y divided by the change in x. In mathematics and physics, the little delta is the Greek letter delta, which means change, so it's a shorthand way to write the change in y divided by the change in x. A second way that may be familiar to you is y2 minus y1 divided by x2 minus x1. Notice the y values go in the numerator and the x values go in the denominator. When we look at trying to compute a slope, what we want to do is to first obtain some information or data. Let's say we have 2 points. Okay, so in this first example, let's say we have the points 3, 7 and -2, 5. To compute the slope, what you want to do is to have the y values in the numerator divided by the x values in the denominator. Now, one of the things you want to be very careful of is when you select a particular point, and it doesn't matter which one you lead with, but when you select a point, and I'll select this 3, 7, you always put the y value over the x value. So I have the 7 over the 3, and I'm going to do the minus and the minus. Then you incorporate the second point, which is going to be the 5 over the -2. When we go about computing this, 7 minus 5 is 2 over, here we're going to have the 3 minus a -2, which is going to be 3 plus 2 is 5. What this physically says is that as x increases by 5, the y value increases by 2. In this case, notice the slope is positive. If we were to go about the process of graphing this, okay, so if we were to graph this line, this would be a situation where it's increasing as you look from left to right being the same way that we read. Okay, so here is an example of a slope. I'll leave it at that, assuming that you are in good shape on this. The most critical thing to keep in mind here, or the most common mistake here, is the situation where people get the x value not under the accompanying y value, but under the other y value, which then gives you the negative of the slope value. And the negative of what you're supposed to have is a problem because you're going to have things going in the opposite direction you want them to. They're going to be increasing when they should be decreasing, or decreasing when they should be increasing. Okay, so be sure that when you take any point, you take the y value, put it over the corresponding x value, the y value over its corresponding x value. Don't reverse the x values. Okay, the second thing we want to take a look at here is horizontal and vertical lines. When we're dealing with horizontal and vertical lines, what's going to wind up happening is you don't wind up with an equation that's very involved. In the first case, let's say we're talking about a horizontal line, I'll abbreviate that as HL. Recall that a horizontal line is going to look something like, well, we'll just work with that. See if we can get this. Okay, so for a horizontal line, you're going to have a situation where the line is something like this or something like this. In either case, notice that the y value never changes. At any location that you choose on this point, okay, whether the location be over here, 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 or here, the y value is always the same. The x can take on any value you want it to, but the y value is fixed. In the case of a horizontal line, the equation is going to look something like y equals 2, which would give me a horizontal line where it goes through the vertical axis at 2. In a situation like this, where the horizontal line is below the y-axis or the x-axis, you get something like y equals, and I'm just making up a value here, -3. However, realize that any time that you have y equal to a constant, what you're actually dealing with is a horizontal line. The second situation that we're going to encounter are vertical lines. With vertical lines, okay, I was going to try and get fancy here. With vertical lines, you now have situations like this. In the case of each of these vertical lines, notice the y value can take on any of an infinite number of different values. Okay, so the y value can be anything. But the x value is fixed at whatever this value is here. Now, I'm not quite sure what x would be. I've not set up a scale on this, but this might be something like x is set to -5, whereas this might be a situation where the line crosses the x-axis at a +4. Notice that vertical lines are defined as x equal to some constant. Horizontal lines are defined as y equal to some constant. All right, third thing we're going to take a look at in this video is the situation where we're looking at a slope-intercept equation of a line. We're getting closer and closer to the point where we're going to actually be able to apply some data and solve some problems. So the slope-intercept. It is quite common in mathematics and most of the sciences for the name of a particular equation or function to be named after whatever it is, or the person who came up with it. In this case, the equation is a slope-intercept equation. That means that this equation is going to have the slope, it's going to have m, and it's going to have the y-intercept. So what it's going to do is it's going to give you a situation where you're going to have a line, and it's going to give you, this equation is going to give you two pieces of information. It's going to tell you how steeply tipped this is and in which direction it's tipped, the slope. And the second thing it's going to tell you is where does this particular line intersect the y-axis. Okay, the y-axis, keep in mind, is the y-intercept. In order to get the equation of this line, we're going to use y equals mx plus b, m here being the slope, and b representing the y-intercept. To compute an equation in the form of a slope-intercept equation, let's start with 2 points. Let's say we have something like the point 3,7 and the point -2, 1. The first step in this If we just follow through on the equation, in the name of it, the first thing we need is the slope. Okay, so the first step in computing this is to compute the slope. To compute the slope, we're going to use y is equal to, it does not matter which of the 2 points I choose to enter into this equation first. I could use the point 37 or the point -2, 1. Either is fine. I'm just going to use the 3 and the 7. Notice, be careful to put the y value in the numerator and the x value in the denominator. It is not an uncommon thing for students to put the x value in the numerator, and that's not right. Okay, now I turn to the second point, which is the point -2. I'm going to put my -2, which is the x value there, and 1, which is my y value there. This is then going to give me a slope of 6 over 3 minus a -2 is 5. That will not reduce or simplify. At this point, I now have part of my equation, y equals mx plus b, in place. I have the slope. It's going to be 6 over 5 x plus b. I still need to compute the value of b. In order to do this, compute the value of b, what I'm going to do is I'm going to take one of the 2 points. It doesn't matter which one. I'll go with the 3, 7 since it doesn't involve negatives and I'm less likely to make a mistake. And I'm going to substitute those values, the value for x being 3 and the value for y being 7, into this equation. When I substitute those in, the y value is 7 equals the 6 over 5 times 3 plus b. At this point, we can multiply, and tell you what, we'll leave this like this, and we're going to get 7 is equal to, remember 3 is the same thing as 3 over 1. So when you multiply these together, you multiply the numerators. The 6 and the 3 is going to give me 18 over 5 plus b. Don't be concerned if the values that you come up with are fractions. That doesn't mean you're wrong. It just means that we're moving further in mathematics and not worried just about integer solutions. In the real world, integers very rarely occur except when you're putting boxes on shelves. You put 2, 3, 4, 5, or 6 boxes on the shelf. But in equations, yeah, you're not going to see integers very often. Doesn't mean you'll never see them, just means it doesn't happen very often. What we're going to do now is we're going to solve for b. To solve for b, I'm going to take and I'm going to subtract the 18 over 5, which means on the left-hand side I'll also subtract 18 over 5. And this can then be written as the equation 7 minus 18 over 5 equals b. Remember, these two subtracted out. On the left-hand side, to combine these two fractions, I need a common denominator. Well, a lot of people look at 7 and say, well, it doesn't have a denominator. It does. Its denominator is 1. To get a common denominator of 5, we need a 5. Well, that was interesting. We need a 5 in the denominator. So I'm going to multiply my 7 over 1 by 5 over 5, which will give me 35 over 5 minus 18 over 5 equals b. Doing the appropriate subtraction, I'm going to wind up with 35 minus 18 is 17 over 5 is the b value. Now that I have the b value of 17/5 and the slope up at the top of the screen as 6/5, I can rewrite my equation where y is equal to 6 over 5x plus my b value of 17 over 5. Regardless what the points are that you're given, the process for computing an equation in slope-intercept form is always the same. Now that we have this equation, we know several things. One of the pieces of information we have is that this line is increasing. We know that because the slope is positive. Okay, the line is increasing because the slope is greater than 0. If the slope was negative, the line would be decreasing. The second thing we know is that the line intersects the y-axis at not x equals, but y equals 17 over 5. Remember, if we're on the y-axis, the x value is 0. So the exact point where this line would intersect the y-axis is the point 0, 17/5. We could kind of sketch out a rough graph of this, something like this. I'm going to need to put a scale in here. Let's see, 17/5 is a little over 3, so I'm going to go up 1, 2, 3, 4. It's going to intersect here at 17/5. A slope of 6/5. 6/5 is close to 1, but it's a little bigger than 1. So it's going to be a little steeper than a 45-degree angle. So I'll draw something kind of like this. And I'm going to want to label my intercept as being 0, 17 over 5. So there's a quick way to get the equation of a line passing through these 2 points. When we look carefully at this, we will find that both of the points, 3, 7 and negative 2, 1, are on this line. Okay, the second form of an equation that we looked at involved the point slope form. You will see as we continue on that I very rarely ever use the point slope form. Personally, I don't find it as convenient to use. It doesn't mean it's bad, it's just that personally I don't like it. Okay, so let's look at this point slope form. Just because I said I don't use it doesn't mean that you're not responsible for it on quizzes and tests and things like that. Okay, so this one, a little bit longer equation. We're going to have y minus y1 equals m times x minus x1. The y1 and the x1 are the coordinates of one of the points that you're working with. Very important, okay? Just in case you're kind of zoned out, tune back in. The x here and the y here are the variables. These remain x and y as we work through the problem. You don't plug in a second point or some other thing and move forward like that. Okay, let's pick a couple of points. In this case, let's say that we use the point 3, 7, and let's say that we use negative 2, 1. First thing we need to do here is to compute the slope. Regardless which form of the equation you're going for, the first step is going to be compute the slope. And in this, I'm going to put the first point, not because I have to, but because I'm just picking it. The y value goes over its corresponding x value, minus, minus. The second point, the y value goes over its corresponding x value. And once again, we're going to get 6 over 5. This should look familiar from the previous problem. It's at this point that we're going to diverge from the technique that we used the last time. In this case, we're going to write our equation as y minus y1. Either point, doesn't matter which one you want to use. To illustrate this, I'm going to use the second point here. Don't have to, I could have used the point 37, so I'm going to have y minus the y value equals 6 over 5 times the variable x minus the x value, which is a negative 2. All right, so at this point then what we're going to do, I'll leave this all visible here, is I'm going to start doing the algebra. First thing is to distribute the 6/5. So I get 6 over 5x. Be careful, this is minus a minus 2, so that's going to be plus 2. So that's going to be plus 12 over 5. Okay, the next step is to add 1 to each side. So I'm going to get y is equal to 6/5 x plus 12 over 5 plus 1. To combine the two fractions, the 1 needs to be rewritten as 5/5. And that'll give us this equation, our 6/5 x plus 12 over 5 plus 5 over 5. And recall, this 1 is the equivalent of this 5 over 5. Now that we have a common denominator, we can combine our two fractions. We'll get y is equal to 6 over 5x plus 17 over 5. Notice that regardless of which of the two techniques we used, after we simplify, we come up with the same equation, 6/5 x plus 17 over 5, and this little square is a mathematical way of saying the end. So that's the end of that one. If we go up to the previous example, notice we came up here on the left-hand side with the same equation, 6/5 x plus 17 over 5. Either way, you'll get the same situation. Okay, which way do I want you to do it? I don't really care. If you're more comfortable using the point slope, that's fine. If you're more comfortable using the slope intercept, that is fine. I will tell you straight out right now, if you choose to use the point slope, I will not accept this. Well, this is not a final acceptable form. Okay, right here. This will not ever be accepted as a final form because it's not simplified, and nothing that we're going to do in calculus will work conveniently using this form. We will always want to get it into a simplified form, with the simplified form being like what's shown up on the top left side of the screen at this point, the point or the slope intercept form. We're always going to want to move to the slope intercept form every time. How you get there, I don't really worry about that. Either way is fine, but your final answers must always be reported in slope intercept form. As we move on in the course, you'll see why the point slope isn't really all that useful. It's just not simplified and you can't go anywhere with it. Okay, the fifth thing we are going to take a look at in this particular video is applications. Let's consider the application listed below. Daniels Discs Incorporated makes discs for Frisbee golf. The setup and operation of the company costs $2,500 a week, and the cost to make each disc is 65 cents. The setup and operation of the company at $2,500 a week may sound a little expensive, but this setup and operation includes things like your insurance costs, your lease, the operation of the equipment, your utilities, the electric, the water, insurance on the company, all of your employee pay, benefits to the employees, etc. So $2,500 a week is a pretty easy number to get to. The cost to make each disc is 65 cents. Now, the first thing we're asked to do here is determine the equation for the total cost per week. Notice this is not per year or per month or anything like that. This is per week. So the units that we're working in for this equation per week match the units in the problem statement. That's not always the case. Okay, so I'm going to list my cost, C of Q, and what I want to do first is to write it out in words so I have kind of a blueprint of what I want to do. Costs, let's say this is going to be total costs, I'll put TC, involves two things. It involves your fixed costs plus your variable costs. You may or you may not have been exposed to these terms before. If you haven't seen them before, that's fine. That's part of the reason for taking this class. Fixed costs are things that you pay regardless whether you make anything or not. Whether the company is open or closed, you're still paying the lease, you're still paying the insurance, you're still paying taxes, you're still paying the employees, you get the idea. The fixed costs are represented by this $2,500 a week. The variable cost is the cost that changes dependent upon the number of units that you're making. So the variable cost in this case is going to be the 65 cents. Now you've got to be really careful here because our fixed costs are in terms of dollars, whereas our variable costs are in terms of cents. We can't have two different units. We have to convert them all to the same unit. It would probably make more sense to convert the cost per disk to something in terms of dollars, and we'll list this as being $0.65. This gives us then the opportunity to write the equation, our fixed cost, which is our 2,500, plus our variable cost, which is 0.65. And something to notice here is that I've already defined my variable. I said the total cost in terms of Q. Q is going to be my variable, so I'm going to do the 0.65 times Q, which means that the total cost for the company to operate for a week is going to be $2,500 plus 0.65 times however many disks we make a week. In part B of this particular question, we're asked to compute the total cost to make 3,000 disks per week. What we're going to do here is we're going to compute the total costs of 3,000 disks. And this is going to be equal to, using our total cost equation, which is up here from part A, we're going to have our 2,500 plus the 0.65 times the 3,000. This is easy enough to plug into your calculator, and we wind up with a total cost then of $4,450 per week. Part C says, okay, compute the revenue. Well, the revenue is dependent on the number of units we sell. And remember that revenue is the selling price times the number sold. Well, in this case, our selling price is $6, and it's going to be the times the number sold, which is the 3,000 of them. This is going to give us a revenue of $18,000. Now, revenue is very different from profit. Recall that profit, and I'm going to put this over to the right-hand side, profit is your revenue minus your cost. What I'm doing right now goes beyond the scope of this particular question. You were asked to compute the revenue. Okay, there you go. But I want to take it further because in any business, the ultimate concern is the profit. In order to get the profit, you take your revenue, which is 18,000, minus your costs of 4,450. And essentially what this is doing is it's saying, okay, we took in $18,000, now we have to pay our bills. And our bills add up to $4,450, which will give us then our profit. Okay, so be careful of that. The last thing we're asked to do, or the next thing we're asked to do here, which is the last thing, is to determine the break-even point. Now, break-even points occur when your revenue equals your profit. Okay, so our revenue, I'm sorry, not our revenue equals our profit, our revenue equals our cost. The last part we're going to take a look at here asks us to determine the break-even point for this operation. The break-even point, I'll just abbreviate this as a break-even point, is where our revenue, the money coming in, is exactly the same as the bills that we have coming in, or in other words, the money going out. So what's coming in equals what's going out. This is an important location for a business to reach. What it essentially means is the business isn't losing money in this situation. There's no profit. Okay, you're getting all your bills paid, but if you own the company, after you pay all your bills and you've worked all week, you've got nothing left for you. You don't even have enough money after working 60 or 70 hours. The last thing we're asked to look at here is the break-even point. This break-even point is the situation where your revenue is equal to your costs. What this means is the profit is zero. Now, a profit of zero is not always a bad thing. You aren't making any money, so if you own the company, you're not making any money. But on the flip side, when you're at the break-even point, you're not losing any money either. Okay. Not a great situation because you don't have any money at the end of the week to take home as your pay. So you work 60, 70, 80 hours, and at the end of the week, you've got not even enough money to buy a hamburger at McDonald's. But at least all the bills are paid. So how do you compute the break-even point? Well, to compute the break-even point, you take your revenue equation, which is up here, actually. The revenue is going to be 6 times the number of units. And we're going to set this equal to our cost function, which is the 2500 plus the 0.65Q. We want to solve for Q. This 6 times Q could really be written as 6Q. Going to subtract the 0.65Q from each side, and what we get is 5.35Q equals 2500. Dividing both sides by the 5.35, we get that Q is equal to 467.28972 something or other. Now, on quizzes, tests, in the real world, when you get a real job, don't go back and tell them we need to make 467.28972 discs. That makes no sense because you can't sell this last part of a disc. You can't. What you need to be careful of here is if you make 467 of them, it's not quite enough. So even though the rounding would suggest to go to 467 because the decimal, the 0.28972, would round down, even though it would round down if we were just doing mathematics, in the real world, if you make this many of them, you're still losing money. Okay, so what you need to have as your break-even point is 468 discs. Be really careful. There are a lot of questions throughout the course where you're asked how many people, how many tickets, how many discs, how many refrigerators. Never report a decimal answer. I would surely hate to have a situation where I'm expecting 367.271 people. That just sounds painful. There is a second way here to look at the break-even point for this particular setup. And that is to go ahead and graph your two equations. I'm going to graph the revenue. Oh, let's put that in yellow. Now remember our revenue equation, our cost equation. I'm going to graph that first, is this 2500 plus the 0.65q. This is in the slope-intercept form. It intercepts the y-axis up here at 2500. The slope is positive, so it's going up, but at a very mild angle. The other equation that we're then going to graph is the revenue equation. Now I've kind of backed myself into a corner here where I don't have a lot of room to work. The revenue equation is 6q. Well, it's a slope of 6, and the y-intercept is 0. This is really 6q plus 0. So the y-intercept is 0. And what's going to wind up happening here is, that doesn't go through 0. I'm going to have a revenue equation. It's kind of like this. So let's say this is my R of Q, and this is my C of Q. The break-even point is right here where the two graphs intersect. Right there is the break-even point. Okay, that is where your cost is equal to your revenue. Now, this occurs at, if we take this on down, Q is going to be on our x-axis, and dollars is going to be on our y-axis. This is going to be right about 468. In reality, this is a rounded value. The exact value is going to be this one, but when it comes time to actually manufacture them, I think you're going to have a hard time selling 0.28972 of a disc. It's a little bit over a fourth of a disc. Not too many people are going to buy that one. Real important concept here, the break-even point. Second real important concept in the upper right corner is the profit. Okay, it's revenue minus cost. And the idea of graphing these two functions, the cost function and the revenue function, finding their point of intersection to compute the break even is a legit thing to do. We'll take a look at that as we progress through the course, but for right now, realize that you can also set it up like we've done here at this point to create an equation 0.535q equals 2500. This way is actually a better way and a more accurate way to solve it, because when you start graphing things, you run into inaccuracies. Hope this makes sense. If at any point in the video things got a little bit difficult for you, you remember you can always pause the video, rewind the video, or replay portions of the video and view things several times as you need to.